Stress concentration affects almost every structure in this world, right from the bed on which we sleep to the spacecraft going to the outer planets. So, knowing stress concentration theory is important for a stress analyst. However, if you take most of the books on stress concentration and try to find out why stress concentration occurs, most of the books are silent on this. So this is where I dug out things from the literature, added my own understanding to it, and in order to explain why stress concentration occurs, I have made this video. If you like this video and want to view similar content, do subscribe to my YouTube channel. Initially, when I tried to learn about stress concentration, I saw some books, but there was some nagging doubt why this stress concentration occurs. So the books were telling how to calculate the stress concentration factor and predict the stress at that region, etc. But when I wanted to understand why it happens, most books were silent. That is one of the reasons why I struggled with this topic initially. So finally, with lot of effort, I read many books, papers, I dug out things, and finally added my own reasoning to come up with this video. If you take most textbooks on stress concentration, what happens is that they are highly mathematical. So when a person starts reading it, most people get drowned in the mathematics and lose sight of the physics of the problem. In order to avoid that, in this video, I'm going to keep the mathematics to a minimum. The emphasis will be more on the physics of the problem. So let me give you a very brief introduction to stress concentration. In most books that deal with stress concentration, if you look at the introduction to the topic, they will show you the example that is there on the screen, a flat plate of uniform thickness with a hole at the center subject to a remote tensile stress of sigma. In our basic strength of materials, they teach us that stress is equal to load divided by the supporting area. So in that, the assumption is that the load is uniformly distributed over the area. So now, if you see here, that is not the case. So let us say the hole was very small, let us say microscopic. So the supporting area is almost equal to the nominal area. So the induced stress should be equal to the nominal stress, right? But that does not happen. So in that case, if the hole is very small compared to the dimensions of the plate, we can see that the maximum stress induced is about 3 times sigma, not sigma. This phenomenon is called stress concentration, where the stress is not uniformly distributed about the area. Instead, are close to the local stress razors like holes, notches, fillets, bosses, etc., the stress becomes much higher than the nominal stress. This phenomenon is called stress concentration. Consider a bar of steel as shown in the figure, having the length 100, width 20, and thickness 10 mm. So it is subjected to a tensile load of 1000 newtons. So as you can see on the screen, the induced stress is 5 megapascals. Now, here we are ignoring the effect of the Poisson's ratio. If we include that effect, then it will become a lot more complicated. So we'll ignore it here. Now let us consider the same bar, same load, but with only difference being that we are changing the orientation of the load with respect to the bar. So now instead of having a bar in tension, now we are having a cantilever beam with a pointed end load. So now from you can see from the screen using the formula that I have given 6PL by BD square. So the stress induced is about 300 megapascals. A big jump, right? From 5 megapascals, the stress has reached 300 megapascals just by changing the direction of the load, changing the orientation of the load with respect to the bar. So what can we see from the TOT experiment? The TOT experiment shows that when we change a tensile load to a bending load, the stress has suddenly jumped from 5 megapascals to 300 megapascals. So, changing the mode of load transfer, whether it is tensile or it is bending, that makes a lot of difference to the stresses. Something similar happens in case of stress concentration. If you're wondering how, uh, continue seeing this video. So now I will be explaining to you with the help of a small case study. So now let us consider a plate without any hole. So I'm choosing a circular region to draw a free body diagram. I'm going to isolate that region and draw the free body diagram for that. So and that region you can see in the dotted lines. So when we draw the free body diagram of that, we can see that the stress induced is still sigma. This is the case one. So let us consider the same problem again. Only thing is that we have introduced a small hole at the center of the plate. So it is also at the center of the region we are considering for free body diagram. So and you can see the free body diagram on the right side. So this particular problem that I have shown here, it can also be modeled as a uh, thick curve beam problem. So what was earlier a tensile problem in case 1, now it has become a bending problem. So the load transfer is through bending near the whole region. So and we had seen earlier that in case the tensile load gets changed to a bending load, the stress increases multiple times. So that is what happens here. And what happens here is that the maximum stress reaches 3 sigma. So in the case study that was shown uh, previously, we saw that the stress concentration is caused by the presence of hole, because the presence of hole causes the tensile load to get locally converted into bending load. Uh, in the example that I have presented, the stress concentration problem is caused by conversion of the tension into bending problem locally. However, that is not always the case for all stress concentration problems. For example, if you have a shaft with a keyway subject to both torsion as well as bending, that it is not tension to bending. However, the examples that I presented here, I hope will help you in understanding the phenomenon of stress concentration intuitively. That is why it happens. These are the references that I have used. You may go through them if you wish.